In this video, I'm going to show you how to create a simulation of a SCARA robot performing a pick-and-place operation inside ProtoTwin. By the end of this video, you should understand how you can create a robot program through the user interface using ProtoTwin's integrated robot controller component. We'll start off by importing the CAD for the robot pick-and-place model directly into ProtoTwin. You can find a link to the CAD in the video description, or you can download the GLTF file for this model from our main website. Now that we've successfully imported the model into the application, we can begin adding behavior to parts by configuring the components. I'll first select the conveyor belt on the left side, and then add a physics component to the belt. If we run the simulation, you'll notice that the belt falls to the floor since it is affected by gravity. To ensure that the belt doesn't fall to the floor, we need to change the body type to kinematic. Also notice how the belt is curved at the end. If we inspect the collider, you'll see that box isn't the most suitable collider type. So I'll change the collider to convex instead, since the convex collider perfectly models the curved ends of the belt. I'll now add a transport surface component to the belt. We can then select the surface of the conveyor belt, using right-click to negate the direction of travel. I'll then add a motor component that drives the transport surface. We can leave all the properties as the default values. I'll now do the conveyor belt on the right side. Once again, we need to add a physics component to the belt entity, then set the body to kinematic and the collider to convex. I'll add a transport surface component again, then select the surface of the belt. We can then attach the motor from the first belt and use the same motor to drive both conveyor belts. I'll now select the case entity on the first belt, then add a physics component. The default values of the body and collider are fine here. You don't need to change anything. I'll then add an interval creator component to the case, which is responsible for duplicating the case on a timed interval, which we'll set to be 2 seconds. If we run the simulation, you'll now see the cases move along the conveyor belt, and then they'll fall to the floor once they reach the other side. This happens because we haven't yet added physics to the stop entity, so it just passes through the graphics mesh of the cylinder. To fix this, I'll select the stop entity, then add a physics component with the body type set to kinematic and the collider left as convex since the stop is fixed in place. I'll now select the emitter entity for the distance sensor, then press Alt-F to focus the camera on the emitter. I can now add a distance sensor component to this entity. I'll configure the origin of the beam by selecting the center of the face. Then I'll configure the direction of the beam by selecting the same face again, but this time with the arrow pointing away from the face, the emitter. I'll also configure the maximum range of the beam to be 0.1 meters. For the visualization options, I'll use the current graphics material when the beam of the distance sensor is cleared. Then I'll use red as the graphics material when the beam of the sensor is blocked. If we play the model again, you should see the color of the emitter change to red when the case blocks the sensor's beam. The sensor also reports the object detected and the measured distance. When the robot drops the case onto the other conveyor belt, we want to remove it from the world when it reaches the end. To do this, I'll select the deleter entity and then add a deleter component to this entity, which will delete the case when it intersects the bounding box. With the conveyors now configured, we can begin to set up the joints and motors to control the robot. I'll start off by selecting the first link of the robot, then add a physics component with the collider set to none since we're not interested in modeling collisions. I'll then add a joint, set the constraint type to revolute, then configure the axis and anchor properties by selecting appropriate features from the mesh. This will enable link 1 of the robot to rotate about the selected anchor point and around the specified axis. I'll now select link 2 of the robot and once again add a physics component with the collider set to none. Then I'll add a joint where the constraint is set to revolute again. Then I'll configure the axis and anchor point by selecting appropriate features from the mesh. If we run the simulation and swap to navigate mode, we can interact with the physics by dragging the mouse. Notice how link 2 of the robot is not connected to link 1. To fix this, we need to reset the simulation and swap back to edit mode. I'll select link 2 again, then we need to set the base property of link 2 to link 1, which specifies that link 2 can rotate relative to link 1. You should now see the joints are connected, meaning the constraints are being applied correctly. I'll now configure the remaining joints. I'll control right-click and select link 3. Then I'll add a physics component with the collider set to none. I'll now add a joint, set the constraint type to revolute, then configure the axis and anchor properties. we need to set the base to link 2, which ensures that link 3 and link 2 are connected. The only joint remaining now is link 4, which will allow the fourth axis of the robot to slide down. I'll do the same thing again with the physics component, but this time I'll leave the constraint as prismatic. For the axis, you need to select it so that it's pointing down. Once again, you need to set the base property to link 3. This ensures that link 4 and 3 are connected. If we run the simulation, you should see link 4 drop, and basically fall forever, since we haven't yet added a motor which applies a torque to counteract gravity. So I'll go ahead and do that now. You can click the Add button to the side of the motor property for each of the 4 links of the robot. I'll leave all the properties on the motor as their default values, since for the speed and acceleration, we'll adjust those for the robot when we add the robot controller component. If we play the model again, you should now see the fourth link no longer falls down, and that we can no longer move any of the joints when interacting with the physics, due to the torque that gets applied by each of the motors. We can now add a suction gripper component to the gripper entity. I'll now configure the origin and direction of the detection ray. The gripper uses a raycast to detect entities within a range. I'll set the range to 2 millimeters, which represents the maximum range at which entities can be gripped. We're now ready to begin creating the robot program. The program will instruct the robot to perform a bunch of movements. You should see 4 teach points depicted by the small red spheres. The robot controller component will automatically compute the inverse kinematics by solving the frame of the TCP to the frame of a target entity. I'll first configure the tool center point on the robot controller by selecting the entity with the name TCP. I'll then set the joint speed to be 1000% and the joint acceleration to be 2000%, just as I hinted at earlier. We can now begin to add instructions to the main program of the robot controller component. I'll first add a joint move instruction, then set the target entity to be TP pick approach. I'll then add another instruction and set the type to a wait signal. However, notice there is no signal to select for the sensor. The robot controller component has its own configurable I/O, which allows you to create variables, or signals, and bind these signals to signals on other components. I'll create an input variable for the sensor and an output variable for the gripper. We can now add a direct I/O connection so that the sensor is bound to the state of the distance sensor component on the emitter, and the gripper is bound to the state of the suction gripper component on the gripper. We can now modify the await signal instruction we previously added to the program by selecting the signal as the sensor. After the sensor is blocked, we're going to want to execute another joint move, but this time with the target set to TP pick so that the robot is in position to pick up the case. Next, we'll add a set signal instruction and set the gripper signal to true, which will turn the vacuum pump on. Now that the robot has picked up the case, we want to execute another joint move and move the robot back to the TP pick approach. Now we want to move the robot to the other conveyor, so I'll add another joint move instruction, but this time select TP drop approach as the target for the robot. We then need to move the robot down, so I'll add a joint move instruction again with TP drop selected as the target. Now we need to turn the vacuum pump off, so I'll add a set signal instruction again, but this time I'll set the gripper signal to false. Now that the robot has dropped the case, we need to move the robot back up to the TP drop approach by executing another joint move. The program is now complete. The robot will first move to the pick approach, then wait until the sensor is blocked, then move to the pick position, set the gripper state to true, then move to the pick approach, then to the drop approach, then to the drop position, and then set the gripper state to false, then back to the drop approach, and then the program will cycle by moving back to the pick approach again. With the model setup now complete, we can finally test the robot by running the simulation one final time. I hope this video gave you a better idea on how to simulate a SCARA robot executing a pick-and-place operation between 2 conveyors by programming the robot entirely through the user interface inside ProtoTwin. Thanks for watching.